In this video, I'm going to show the image of why we need the Continuous Time Linear Equalizer CTLE in the SerDes system. Before why, what is the Continuous Time Linear Equalizer? Before understanding the Continuous Time Linear Equalizer CTLE, how do you identify the equalizer as either discrete time or continuous time? Any circuit image? Bingo! Clock. The discrete time comes from the clock. If there's a clock, that's a discrete time equalizer. If there's no clock, that's a continuous time equalizer. What does the linearity mean? Think about a simple mathematical image for 5 seconds. Exactly. The straight line in the transfer function of the Vout versus Vin implies the linear relationship between the output and the input. In other words, the output was proportional to the input if the relationship is linear. On the other hand, you probably can find lots of nonlinear images in your head. The left-hand side shows one of the nonlinear examples for you. The output will be plus y if the input is greater than 0, and the output will be minus y if the input is less than 0. Again, the output magnitude was not proportional to the input magnitude, so the relationship is nonlinear here. Once we understand what the continuous time and linearity mean, we can combine both characteristics together to get the continuous time linear equalizer idea for our usage. The first item related to the linearity is the gain over CTLE as an amplifier. We like the gain of Vout over Vin or M to be greater than 1. Remember, the equation is needed due to the channel loss, so the gain can compensate for the loss at a high frequency and boost the output swing of the equalizer or input swing of the sampler. As we mentioned in Y equation video, increasing the input swing of the sampler will help the sampler to make the right decision and reduce the bit error rate in the data transmission. The second item related to the continuous time is the simplicity with less issue in the circuit implementations. Without clock in the discrete time domain, we don't need to generate or dispute the clock, which will burn more power and consume some chip areas. What could be the challenge of the discrete time equalizer? Think about the image for 5 seconds. As mentioned before, the discrete time equalizer must require the clock, and that's the challenge with the sample and hold sampling events. First of all, the clock structure is quite important to make the sample voltage accurate enough such that the equation can be effective without extra distortion. Reasonably, more power is needed in the low jitter clock generation and clock distribution. In addition, the clock feed-through could be a concern to interfere the input signal of the equalizer. Therefore, the continuous time equalizer without clock and sampling would be preferable in the equation architecture topology. As we discussed in the Y equation video, you can put the equation block either before or after the channel, depends on how you implement it. But for the CTLE block, what would be a good place for it to go? Think about the CTLE placement image for 5 seconds. Good. Putting the CTLE after the channel is the best. But what's the reasoning behind it? I will summarize the most 3 motivations below. First, the channel's interface is an analog signal, and the CTLE is analog in both the time and voltage domains, so the analog compatible signaling is a perfect fit. Second, as mentioned in this video earlier, the CTLE is an amplifier, which the gain can compensate for the loss at the high frequency and boost the output swing right after the channel. Therefore, the CTLE increased the signal-to-noise ratio SNR at the receiver front end and helped drop the burn dramatically. Third, the CTLE at the receiver input is very power and energy efficient, since its output would be connected to either another amplifier or sampler. Either one output impedance of the CTLE would be high impedance, and the required current would be small to get the reasonable output swing. Let's look at the CTLE in the frequency domain as a case study. In this example, the channel loss is 17 dB at the next rate 5 GHz of the 10 gigabit per second data rate. In addition, the frequency response of the channel is like a low-pass response as we discussed in another video. In order to equalize the channel's low-pass response, the CTLE must provide a high-pass characteristic at least up to the next rate, which is the peak gains frequency. Therefore, the compensate bandwidth of the channel plus CTLE is wide enough, at least greater than the 5 GHz, next rate of the 10 gigabit per second here. But please advise that the maximum gain of the CTLE is limited. Therefore, the peak gain was chosen at a high frequency close to the next rate. Instead, the DC gain of the CTLE would be reduced to equalize the gain at the low frequency and high frequency of the total frequency response. Hopefully, the continuous time equalization in the frequency domain will make sense to everybody. Another important item that should be mentioned is the CTLE has a limited bandwidth in the case study. Remember the equalization image we've talked about in the white equalization video, as shown on the left image. The left image only exists in the mathematical world, but in the real amplifier circuit or the CTLE, the gain should be dropped at higher frequency and has a law of curve at the right. So, the total frequency response of the channel plus the CTLE would be bandwidth limited, such that the output of the CTLE still has some residual RSI and the signal won't be exactly the same as the channel's input. Here is the output waveform of the channel. For the long-run pattern of the data bit stream, the data is mostly low-frequency content. The loss should be very little, and the corresponding swing is the largest. On the other hand, for the 1010 clock pattern of the data bit stream, the data is mostly high-frequency content. The loss should be the largest, and the corresponding swing is the smallest. Therefore, from the time domain waveform equation, what waveform image after the CTLE do you want to have? Think about the image for 5 seconds. Exactly. First, you want both long-run and 1010 clock patterns to have equal voltage swing, which was the signal equation in the time domain. Second, you may want to increase the high frequency swing to make the sampler has a better sampling margin to make the right decision. On the other hand, the low frequency swing was too big, and that's okay to reduce it to some swing as the high frequency one. Please be advised that the high frequency gain of the swing would be the maximum available gain for the swing. So, the DC gain should be adjustable, and let's go there after a few minutes. In summary, the CTLE's linearity can be improved by reducing the dynamic range of the minima and maxima swing. As you can see, the original swing range is huge between different bit stream patterns, but the swing's dynamic range can be reduced by the CTLE. Then the CTLE's linearity would be improved further by what both low frequency and high frequency swings range are equalized and minimized. In the time domain, we can look at the single pass response and get some images related to CTLE. In this example, a single pass Vin is applied at the lossy channel's input, and the single pass acts after the channel has a long tail postcursor and one bit precursor. Therefore, the CTLE will sharpen the transition and reduce the magnitude of the precursor and postcursor as small as possible without interfering with the previous symbol or the following symbols. The CTLE's output Vout also allows all the cursors except the main cursor A0 are reduced greatly, which means the ISI was minimized to some extent. In the last view of the time domain, the bitstream response over images should be verified for the CTLE's performance. Usually, an I diagram will be evaluated through tons of bit overlap to check the I width for the timing margin and the I height for the voltage margin. As you can see, a wide open IV in is applied at the channel's input, and the IX after the lossy channel is closed. The closed I implies the bit array could be very significant. Therefore, the CTLE is a must to recover the I's quality to some extent, like the I at the Vout, which is open and feasible to achieve a very low bit array if the sample point is at the middle of the I. Let's look at some practical channel response, like the Hitachi DAC cable. As you can see, the frequency response is low-pass characteristic, but the loss level varies in different lengths of cables. So, for different channels response, the CTLE's frequency response must adjustable to the inverse of the channels closely. In other words, the CTLE must design to be highly programmable to adjust the response accordingly. Lastly, for the realistic CTLE response, the peak gain at the high frequency is the maximum available gain, which is almost the same over different settings. But the DC gain can be reduced or thrown away to a different level for different loss levels of the channel. Here is the summarized image you may have for a CTLE's advantages in the equation, which can well explain why you need the CTLE. For simplicity and less design challenges, the continuous time without clock equalizer is preferable. The linear gain or amplification at the high frequencies is a must after a lossy channel. So, both combined continuous time and linearity may tell you why the CTLE is needed. For the CTLE's placement, putting it after the channel is the best due to the several reasons, and you might want to recall or think about that for 5 seconds by yourself. In the time domain image, the CTLE's single pass response also shows you that the CTLE can cancel not only the precursor ISI, but also the long tail postcursor ISI, and those are the strengths of the CTLE compared to other equalizers. Please be advised that this video is to show the image of why we need the Continuous Time Linear Equalizer CTLE in the SerDes system. So, all the circuit images are related to the advantage of the CTLE here. I will show other circuit images of the CTLE's weakness and how we can mitigate those issues later. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.